Okay, hello, welcome back everyone. So we're going to get started. We're going to talk about AdSense, and then we'll drift into some peripheral topics like APIs that are relevant to advertising. So we just finished talking about AdWords, which is where Google shows ads along with the search results. AdSense, on the other hand, is a model where sites not affiliated with Google can agree to let Google run ads on their sites. Now, this creates a number of interesting problems. Number one, there aren't search results to tell Google exactly what people are looking for, so picking the ads is going to be a little bit harder. Number two, in most cases, people are only going to allow Google to display, say, one ad per page, as opposed to Google's standard operation where they're showing ads along with search results. There can be many ads on the page. So the process is similar. There's still quality scores for ads. There's still a bidding process, but the details are a little bit different. So let's get into the slideshow. AdSense is a customizable model for advertising revenue generation. What it's a lot like is getting ads in a newspaper, if any of you remember what a newspaper is. So fundamentally, people can agree to let Google run sites in a predefined, Google run ads in a predefined portion of a web page. So they say, here, run a 200 by 200 pixel ad in this corner of the page, something like that. And again, it's a lot like how it gets mapped out if you call up the newspaper and say, hey, I want to run a quarter page ad for a couple days. So difference is AdSense allows micro customization. So essentially, every distinct user who views a page could get a unique ad custom tailored for their experience, as opposed to a regular newspaper that they're going to print out 1 million copies and they're all going to be basically the same. So, revenue model. Site owner agrees to display Google's ads. Google selects and provides the ads in the appropriate place on each page. And when viewers click on the ads, they pay Google, and Google gives a cut of that to the site owner, typically about 40%. So if you're some kind of unemployed blogger and you say to yourself, well, I'd like to make money to have pizza once in a while, you can write your little blog and you can have ads on it, and hopefully once in a while somebody clicks on them and Google will pay you some money. So basically this solves the problem of earning revenue from free content, right? This was always an issue in the early days of the internet. People understand how it works on TV. You watch broadcast TV for a while. Every now and then it gets broken up that you watch some commercials. The advertisers hope they're getting their money's worth, but that's basically what allows the TV to be provided free. Problem is, unless you can do a reasonably good job of targeting your ads to your viewers, then it's going to be actually not only worthless, it'll be worse than worthless. So first of all, if you show ads that aren't relevant, people are going to stop clicking on them, right? They're not even going to click on them in the first place. But what happens? So you come up with some desperate tricks. Like this is one of the things you used to see a lot in the late 90s. There would be these big flashing ads that would say, congratulations, you're the millionth person to see this page. Even though the page view count in the corner of the page said something like 20, there would still be this, bright blinking banner ad that said, click me. Well, one time my curiosity got the better of me and I decided to click on one of those. I knew but it said something like, yeah, go through these pages and you will get some prize that's worth like a few $100s. I forget. It could have been cash. It could have been an iPhone, something like that. Well, they didn't have iPhones back then. Anyway, some cash or piece of technology, something like that. So I clicked on it, and after going through about 20 screens of basically asking for as much personal data as I was willing to give out, eventually I said, yeah, no, I'm not going to do that, and I quit. And that was the end of that. And I never clicked on one of those banner ads again, which is why I say they can be worse than worthless. Not only do you look at them and say, oh, I'm not clicking on that, that's kind of worthless. But when you say, I'm never going to click on an ad like that again, that's what makes it worse than worthless. Okay, now for AdSense, again, because they don't have search terms, Google has to come up with some way to define what the site is all about. And that's a lot trickier. So essentially, you have some tags on your site that describe the site content. The ads also have some tags that describe what the ad is about, and Google tries to do a reasonably good job of matching the two. But this matching is less precise because, anytime you're doing tags, it's categorical. So there's only so many groupings. Google's going to try to do a good job, but it's not going to be perfect. The other thing, people often visit the wrong site. right? We click on the wrong things all the time, but it's a lot easier to end up at a site you didn't mean to go to than it is to enter the wrong search terms, right? It's very difficult to type in something entirely wrong that's not what you're looking for. But even though it generally doesn't work quite as well as AdWords, it doesn't have to be perfect. It still works well enough that Google can make money off of it. Anyway, AdSense is very popular with bloggers, right? People that are providing free content but want to make a little bit of money off it. Promotion aggregators, so think of your kind of sites like Travelocity, Priceline, things like that. Any sort of coupon-based site, and other informational sites. Any site that basically doesn't have a product that they're selling but still wants to make money off their website, yeah, AdSense is a reasonable way to go. So, basic diagram, again, advertiser sends ads to Google. Google has a database full of ads that it's pulling stuff from. Google also has a database of web pages. So anytime somebody views a page where Google has space to put in its ad, these green boxes, Google's going to pick some ads. It's going to show them in the appropriate places that have been permitted by the site owner. And then if a viewer clicks on one of those ads, eventually the advertiser will pay Google, and Google will give a cut to the web page, typically around the order of 40% or so. Web age, there should be a P there, web page. All right. Now, there are different payment models for clicks. So the most common one is pay per click, right? Google gets paid when the ad is clicked. But there are some other ones. There's one called pay per impression, where anytime an ad gets shown, Google gets paid for that. And that makes sense for a lot of things that aren't going to lead to an immediate purchase. For example, if there's a movie in theaters, right, you might see ads for that on other sites, but nobody really expects that you're going to say, oh, that movie's out now. I'm going to click on that ad and go buy tickets right now, right? Most people don't do that. Or if it's, say, an online ad for McDonald's, nobody's going to get on there and say, oh, yeah, I was browsing for tech support for my iPhone, and I saw this ad for McDonald's, and yep, I'm getting in the car and going to McDonald's right now, right? Or I'm going to McDonald's and ordering delivery from them. It doesn't work like that. But those companies that still want to advertise, basically they end up paying a little bit for every pair of eyeballs that sees the ads, and that's called pay per impression. The last one, sometimes advertisers can take a very cautious approach and only agree to pay when the sale actually happens. So that's called pay per conversion. A conversion or a goal conversion in web analytics is basically somebody doing something you want to happen, and it's typically associated with either a sale right now or a sale that you expect to happen in the future. Now, pay per click is the most common. It's a good balance of risk. So on the one hand, pay per click, there's a little bit of risk to the advertiser, which is that you can pay for clicks, but they don't end up actually buying something. So that's the risk there. And Google has a little bit of risk, which is Google shows the ads, but they only get paid if someone clicks on them. So pay per impression, there's essentially no risk for Google. Google knows it's going to get paid. On the other hand, the advertiser, there's more risk on the advertiser that they don't know what they're getting for their sales, for their advertising. Pay per conversion, on the other hand, Google's basically taking on all the risk. And the advertiser is essentially not taking on any. They're saying, well, unless we make some sales off of this, we're not going to pay you. But as anything, the greater risk you take, the also, you have to be compensated for that. So if Google's taking on all the risk, they're going to charge you a higher rate for this kind of pay per conversion than they would if it were just pay per click, right? Likewise, they're not going to charge you as much, effectively for pay per impression as they would for pay per click because you're taking on more of the risk. So that's what's going to drive some of these rates. So for example, right, pay per click might be $1. We can look at what the fair numbers would be. That's some stuff from last night. Okay, so fair numbers. Suppose the advertiser gets a 10% click rate, right? Click-through rate, we'll just use the technical term. Click-through rate on an ad. 10% of clicks lead to a purchase of about $100, right? We'll call that profit. So 10%, for every person that sees the ad, 1 in 10 of them is going to click on it. And of those clicks, 1 in 10 is actually going to buy something. So a fair price, pay per impression, would be $1, right? Then that would be a break-even prospect. So 10% of the people click on it. Of those 10%, only 1 in 10 actually buys something. So 1% of your viewers are actually going to click and buy that $100 thing. So pay per click, right? Fair price pay per click would of course be $10, right? Because again, 10% of the clicks, however many clicks there are, 10% of them are going to make you about $100. And of course, fair price pay per conversion would be $100, right? That would be, and of course, all these are maximum prices. Maximum sustainable prices. But of course, the advertiser wouldn't pay that much. Well, typing's hard today. The advertiser wouldn't pay that much because no profit would be left over after paying for the ads. Okay. So hopefully that all makes sense. Anyway, so pay-per-click is the most common, again, because it's easy to track results and it's a good balance of risk. Click-through rates, though, are notoriously low. Even if you have a well-targeted ad that's showing along with search results, if you're getting 3% clicks on that, that's actually really good. For most other online ads, for untargeted ones, typically way less than 1%. So around the order of 0.1%. And you can think about that yourself, right? If you're out looking around on other random sites, you see lots of ads all the time. How often do you click on one, right? Most people hardly ever do. So yeah, that 1 in 1,000 sounds plausible. Okay. Now, what does Google want? Google wants everyone involved in the advertising process to be happy. How are they happy? Well, viewers are happy if they see ads for products that are relevant to them, things they might actually want to buy. Advertisers are happy if people click on the ads and go to their site and hopefully eventually buy something. And Google, of course, is happy if they make bags and bags of money. So how they get happy, again, if Google can show ads that are relevant without dragging down search result quality or without, completely making it difficult to see where the search results are, then viewers are happy. They know, Google search is a free service. Yeah, there's going to be some ads along with that. Advertisers, on the other hand, right, they want to pay for traffic that's likely to buy stuff. If they're getting junky traffic that's, going to their site but not buying anything, they're not going to be happy in the long run. And Google, of course, makes itself more happy if it can show highly relevant ads for a particular context, right? So ads that are appropriate for a set of search terms or ads that match well with the kind of content on a page. If Google can do that well, it's going to do a better job of showing ads that are interesting to customers. Customers are more likely to click on them and buy stuff, and then Google will make more money because it's providing more value to the advertisers. However, with just a little thought, right, you could probably think of some vulnerabilities in this model. For example, what if the unemployed blogger, the site owner, clicks on his own site's ads, right? He says, hey, I'm unemployed and I'd like to have pizza tonight. So if I'm getting $1 per click, I'm just going to click on that ad 10 times and I'll get the check in the mail. Or alternatively, what if customers click on competitors click on an advertiser's ads, right? So for example, Target and Walmart, they're bitter enemies, and Walmart decides to write up a script where anytime it sees a Target ad, right, it browses the web and looks for Target ads. Anytime it sees an ad from Target, it does a virtual click on it so that Target has to pay, even though it's a bot doing the clicking, and there's no way that's actually going to turn into a sale. So because of problems like that, I'm not saying Walmart does that, but problems like that, concerns like that, Google needs to distinguish between legitimate and illegitimate clicks. So key elements of doing that: number one, figuring out the volume of traffic at the source of the destination. For example, if you're an unemployed blogger and you've got your little blog site and you're running AdSense ads on it, and you click like 10 times within a minute, Google's going to figure that out. Google's going to say, oh yeah, that's bogus traffic, that's not real. Other things, the time between clicks, right? So for whatever reason, if you have a long string of clicks within a fairly narrow window, Google's going to think something suspicious about that, right? normal people, they go to a site, they might click on an ad once in a while, but if you're showing up and you're clicking on 10 ads a day, every day, even if it's all like not within a super tight window, nobody clicks on that many ads. Google's gonna say, something's up with this. And of course, behavior on site. Normal site users, they show up to a page, they look around for a while, they take their time. Yeah, maybe once in a while they click on an ad, but mostly they're there to look at the site. But if Google sees traffic that it goes straight to the site, clicks on a few ads, and then goes away, again, Google's going to say, oh yeah, there's something up with that. That's not how real humans act. So any of those clicks that are deemed illegitimate, that basically fake traffic, they're not going to earn any revenue. The advertiser doesn't pay Google, and Google doesn't pay the site as applicable. Okay, so now we're into application program interfaces, or APIs. So an API is an interface between applications based on standard input and output formats. Okay, so it's going to be something like this. I'm going to put a little box here. I'm going to label this API. API. So for example, on one side, you have, say, Google. So Google's ad system, whatever it may be. Over on this side, you have your browser. Okay, we'll put a box around that. Now, the thing about the API is going to ensure that both sides are speaking in the same language. Okay, I'm going to draw a couple arrows. So, for example, one of the things that Google sends to the browser sends the ad. Okay, so it sends the ad for that, and it also sends the link embedded in the ad. So if you click on the ad, you go to the proper place. The browser, of course, expects an ad in a standard format. Okay, which Google is going to provide. But as long as the ad's in that standard format, that's great. The browser can display it as necessary, right? So if somebody does click on the ad, well, guess what? They go to the proper site. But it's also going to send some analytics data to Google so they know that the click happened. Okay, so that's a thing. And then, this arrow should be going the other way, shouldn't it? Better. Okay, so then Google will know, expects analytics data in a standard format. Okay, so the API is just making sure that the data is in the correct format. So Google's going to send the ad in a standard format. The browser knows that anything that it receives through that API, it knows what format to expect the data in. So it can get that string of data and format it properly to an ad that displays in a proper portion of the page. Likewise, anytime that kind of action occurs on the browser side, it can send some data back through the API to Google, and it'll be in, again, the standard form with all the things that Google needs, and Google will get that, and it'll be in the correct format, and it can be processed and unpacked correctly. Okay. So what this APIs use, generic objects that conform to standards, right? So there's a standard set of data around an ad. So it could include things like, the ad could include simply a link to a file, but that data's got to be pulled from somewhere. So at the very least, it needs a source link, right? Where to find this in Google servers, pixel size, probably a duration, right? A link through the ad, that sort of stuff. So all these basic things that are in the object, yeah, that's what Google's going to provide. Likewise, the analytics data that gets sent to Google, it's going to, analytics data could include the source page, right? What else? The time of the click, perhaps. What else? We know the name of the ad, so we know that's what's being sent, right? Or its reference, somehow that Google can recognize which ad got clicked on and the user who clicked the ad, okay, to the extent that they have information about them. That might be as either via a cookie, right, a data file stored on the computer, or an IP address. Okay, so stuff like that's going to get sent to Google. All right. So ad APIs, the nice thing about it is that people that design these APIs, they don't need to know machine-specific details, right? They don't need to know what operating system the browser is on. They don't need to know what browser is being used. Regardless, this data appears in some standard format that's entirely independent of the browser that's receiving it. Likewise, the browser sends the analytics data to Google. It doesn't need to know any details about how Google's ad system works. It just needs to know, well, if I send the data in this proper format, Google will know what to do with it. And that's all I need to worry about. Okay. So API formats, what are the essentials? Well, first of all, they're going to need the description of the object itself, right? So for an ad, it would be the data it holds, where to find it, any actions it can perform, like if you click on it, what happens. If there's a video playing involved, you can pause it, you can resume playing, stuff like that. And then the formats for the inputs and outputs. Now, these objects that get sent along through APIs, they can be provided, you know, in our object description languages we talked about a while back, either as XML, which is workable but out of date and not really used much these days, or JSON, right, which is that JavaScript compatible one. And the nice thing about JSON is it's compact and thus primarily for that reason, widely used. Okay. Now, all these ads are going to be objects. So, for example, you may have sometimes looked at a product on Amazon, and then within an hour, you start seeing online ads everywhere for it. Well, Amazon also has a standard advertising tool, right? It has the Amazon Ad API. So, any site that agrees to run Amazon ads, guess what? They're going to look at the data on your machine about what you've been looking at Amazon. And Amazon's going to pull that data to display an image of the product that you just looked at. So the basic inputs, user history, right, whatever you did while you were on Amazon, and that can be grabbed from a cookie. Again, small data file stored on your computer through Amazon. Various actions that are permitted, right? So pulling the current ad image, so whatever product it is that you looked at on Amazon, it's going to pick, you know, its top image for that and show it in the ad. It's going to be able to display the image. It's going to recognize that clicks are going to lead to that product page. And then the output, whether the viewer has responded or not responded, right? Did they click on it? Did they not click on it? It could check to see if you hovered your mouse over it for a while, if you thought about doing it, how long you stayed on the page that the ad was there. Any of those factors could potentially be sent along as analytics data. And of course, if you see the product and ignore it, that can update the cookie and affect future ad displays, because Amazon doesn't want to keep showing you the same product over and over and over if you've seen it like 6 times and you're not going to buy it. So at some point they say, well, maybe we'll show you something else. We'll see what we can, you know, learn about what might be interesting to you. Okay. Google's databases. Google has massive databases for advertisements, for storing how users respond to ads and search results, cached web pages, web analytics data, and lots more. They have untold exabytes of data. In fact, you can take a peek. Let's see if they, I don't know if we'll even be able to find this, but I'll try to look it up. Let's see, how many exabytes of data does Google have? Now we're there. Let's see if we can figure it out. 10 to 15, okay? But that is from a few years ago. That's from 3.5 years ago in 2017. So let's say it's probably, you know, maybe around the order of 20 exabytes now. That's a tremendous amount of data, right? So they say here this number, about 30 million PCs combined. Yeah, that's a lot. Okay, where's my Facebook stuff? Okay. Anyway, it's perhaps surprising considering how big the scale of Google's system is, but Google's advertising runs on what's called extended SQL. So they call it new SQL. So basically, the syntax is like SQL, but the data is structured in some special ways that allow Google to process certain actions faster. The base platform for Google is one called Spanner. On top of that is F1. That's where Google stores the advertisements. All right. Now, before we get into this, we'll talk about why big data is a problem. So, first of all, main feature of relational databases is that you can do join operations, and that's essentially the mechanism where you can join data from across tables. Now, the way this works, the way a table join works, basics of table joins. Okay, essential to multi-table queries. All right, so imagine if you have one table of customers and another table of invoices, okay? And you have a very simple question. You want to ask which customers from the Chicago area have bought product X in the prior month. Okay. Now that's going to require data from both of these, right? So we're going to assume these are linked, basically that every invoice has a customer field, right? So that makes sense. And the customer has zip code. Okay, so that's how we learn if somebody's from Chicago area. So basically, the way these tables get combined is for every customer, right? One way to do it, for every customer, check if they're from Chicago, then extract all the invoices with that customer ID. Okay, so you look here, here's a customer. Is this from around Chicago? Yes. If so, scan through this invoice table and grab every one of these that has, every invoice from the appropriate time period that has that customer in it, right? Or you could do it the other way. For every invoice, check if what? Check for the date and product, and if you find it, cross-check that with the customer zip code. Okay, that one, odds are that's probably faster, but it's hard to know for sure without, detail about the systems. Anyway, the point is, in a sense, you're cross-comparing the entire two things of the tables. Now, certain join operations are very, very big. Certain joins, what are called outer joins, are very data intensive. And what they do, they essentially multiply the two tables together, right? They're not looking at a subset. So where you would do this, this is necessary to check if every record in one table has a valid counterpart in the other. So in this example, e.g., every customer in invoice actually exists. Okay, because every invoice could have a customer, but you might have deleted customer records or entered it incorrectly, and it's just not there. The way this is done in practice is essentially you take this customer and you blow that up across every invoice here, and you say, oh, does this match? And then you take this second customer and you blow it up against that invoice, and you look and see, does that match? It's a big headache. There are more efficient ways to do it, but that's the way an outer join works. And the time you do need to do that, if you need to comb through both tables completely and create one giant mega table so you can see if everything in there is actually valid. So that kind of operation is very big, very data intensive, and can easily expand beyond the reach of a single machine. Well, what happens if you're crossing machines? As long as these operations, as long as these big database operations are happening in RAM, they get processed reasonably quickly, right? Typically less than a few seconds, even if they're pretty big tables. However, if the tables span multiple machines, the data interchange happens at network speeds, much slower. Okay, so what happens is once you cross that threshold where these tables are so big that combining them in some way can no longer be done on a single machine, then the database operations suddenly and dramatically slow down. It's a big problem. There have been businesses, they're doing this on their own hardware, and when they switch to some cloud-based database system, queries that might have literally taken a week are now being done in, fraction of a minute, just because they have more capacity, they can process the data smarter. Okay, so that's what there is to know about database joins. I mean, it's kind of a technical thing, but the problem is database joins are necessary to compare data from multiple tables, but doing that is potentially a very data intensive operation that can happen really slowly. It can take a long time. Now, anyway, so again, it is a little bit surprising that Google's using a SQL-based system, but they're not just using ordinary relational-based systems. They do something called NewSQL that basically allows Google to do more targeted operations. So instead of involving entire big tables and multiplying them together, Google's a lot smarter about picking what data it needs from which tables and only cross-comparing that. Okay. So Google Spanner, it's a system that essentially uses SQL syntax, but approaches NoSQL performance levels. The nice thing about it, the main feature, it's almost immediate consistency. So if Google has multiple copies of data, they're almost instantly synced up and correct, which makes it suitable even for things like transaction processing. The nice thing, since it's essentially a SQL-based system, businesses can migrate their databases in their current format without having to rewrite any of their database code. They can still use standard SQL and don't have to update anything. All right, so a simple map out of this, how it works, where it lies on this. Let's slideshow this. So your traditional relational database management systems, they're great as long as the data isn't too big and the database schema are more or less permanent. That is, the set of fields and formats, if all that doesn't change, you can have your carefully calibrated database and it'll work well. And as long as the database tables aren't too big, you can retain any combination of them in RAM. It'll still get processed pretty quickly. On the other hand, you have your NoSQL systems, right? They're very fast and they're very flexible. It's very easy to change, for example, the data in a key value store, but it creates problems in terms of inconsistency. For example, you could adopt an eventual consistency approach. Also, if your database schema are changing frequently, one of the things you're probably going to lose is the ability to process queries across multiple tables very quickly. So again, consistency guarantees aren't always there for NoSQL systems, but they are fast. So Spanner, it still tries to be fast enough, right? It's fast enough, but it also gives strong consistency guarantees. So it's kind of in that middle ground there. Even if you're changing things, if you're changing how your database is set up, that's not going to be a huge problem for Spanner because they're used to dealing with things at that kind of scale. It's already designed to run pretty fast. And it can even do joins of large distributed tables, so tables that are broken up across multiple machines. It's designed to be able to handle that as well. Okay. Now F1 is Google's database storing ads. It is a very big relational database system. It's also highly consistent despite being a large-scale distributed system. That means, unlike Facebook, where things are typically processed as being eventually consistent, Google says, no, we need to have strong consistency guarantees. So if something in one copy of data gets changed, it's basically instantly reflected in all copies. And like NoSQL databases, it's scaled to run on many instances of standard hardware, right? It's not something that's optimized for a particular set of hardware or requires especially high-end, cutting-edge hardware. Instead, it runs on large numbers of pretty much standard low to medium-end hardware servers. Key operational properties, well, number one, reading should be fast. It shouldn't slow down the delivery of search results. That's the big thing. If Google's going to show ads along with the search results, they don't want the ad delivery process, the retrieval process, to slow down how users see the ads. Write speed, it's not really that important, right? If an advertiser uploads an ad and it takes, a few extra minutes to upload, well, whatever. Advertisers don't load up that many ads compared to how often people search on Google. Also, F1 is based on Spanner and Bigtable. So Spanner is Google's core system. F1 is, structured into that. It can also use Bigtable for the reasons we talked about before. For, data that has different elements that aren't always there. So remember we talked about Bigtable in terms of web pages. The two key things, you can have groups of related fields, and you can also have, if you have sets of fields that are zeros, you can zero them out pretty easily. So again, depending on the type of data that's being tracked for particular ads, some of that analytics data may be tracked for some ads, but not for others. So it's handy to have those zeros in there. Okay, but the number of ads Google's running isn't that many, right? I mean, the video content is there, but compared to the number of web pages Google has, yeah, the number of ads is pretty low. All right, another feature that Google has, another system, something called BigQuery. So BigQuery is a system that allows fast queries involving very large tables. So when I say very big, I mean, potentially tens of millions of rows. Now, if you're interested, I have a few links on there, but that's what BigQuery is. And it's a very useful specialized system. If you're a business that has these gigantic database tables, but you fundamentally don't want to be in the business of designing your own custom databases, then BigQuery is wonderful, right? You show up, you use it, it's there for you. And it's, again, much cheaper and simpler than building a comparable proprietary system from scratch. Downside is, of course, even BigQuery has its limits. So it is possible that your database operations are written and structured inefficiently, and you try to send some big database table to BigQuery and run queries on it, and it just doesn't work fast enough. Generally, the cutoff is if a query can't be completed within 30 seconds on BigQuery, then it says, nope, you got to figure out something here. This is kind of a mess. It's too big for us. Okay, so simple ways that works, for example, one possibility, right? Suppose you want to do Suppose you are joining two tables. One is very large, say 50 million rows. The other is pretty small, say 10,000 rows. Okay? If you're doing one of those big outer joins, right, so the full-blown big outer join, that could be 50 million times 10,000 equals 500 billion rows, which is a big problem for any standard hardware, right? With like a 1 terabyte drive, 500 billion rows, that's not gonna, unless the rows, you won't even have enough space to store the key fields. So instead, Google can slice up the very big table into what? Something like 10,000 slices, each of 5,000 rows. Then the combined table is just what? Even if we're somehow multiplying them together, that combined table is just 10 times 5 million, right? 50 million. Probably manageable, right? If the organization could keep 50 million rows on one machine, well, then the combined table could be, 10K times 5K. That's probably manageable. Or depending on the type of query you're doing, what I mentioned in the slides, or depending on the query type, right? you could slice the big table, which is slow to process anyway, right? Because it's going to have to all get run on one machine. That could take a while. You could slice the big table into, say, 50 slices, each running on a separate server of 1 million rows, and attach the complete copy of the 10K row table. And then, right, basically each server involved gets 1 million, well, 1.01 million, 1 million plus 10,000 rows to handle. So it's not so bad. So anyway, depending on what you're doing, what your database needs are, how the queries are structured, this is a pretty standard technique. One big table, one very small table. You could slice the big table and send along a complete copy of the smaller one. Okay, so again, the process is like Hadoop's MapReduce that we talked about before. And then at the end, Google compiles and returns the query results. So the basic process, the way this would work, right, again, with Hadoop, MapReduce, whatever, would be something like Google has this massive set of data and a stubby bit of data, right? So this is our big table, this is the little one. Each of these, right, gets broken into however many slices. The big table gets broken into slices, okay? And this query, right, this one gets attached along. Whoop. Why did I do that? Each one of these gets attached along as appropriate over here, okay, and so on. Now for that, each query runs set. So here's the total database tables, okay. Each server runs the query on a slice of the big table, and then all the query results get recompiled, combined and delivered to the user. Okay, so all these are brought back together, everything from here to here. We have this match of query results, and that's it. Okay, so if it's, for example, this is a table of invoices, which could be very large. This is a list of customers, which is very small. We want to run some query on that. Well, I can slice this. I can send each server a set of invoices, okay, and then the list of customers, whatever I'm looking for a zip code, whatever. And same thing here, invoices, customers. And then here I can say, at the end, I have set of matching invoices gets delivered. Okay, and this is how you can decompose a big problem like this, break it down into smaller pieces that, you know, again, if I run the query separately on each slice, the net total of results is still going to be the same as if I ran it all on this one big table on one machine. Okay, so same results delivered much faster. Okay. Now, key difference between BigQuery and Spanner. Well, they sound similar, right? BigQuery can process a lot of data very quickly, but so can Spanner. So what's the difference? Well, Spanner is very, you require a lot of frequent but fairly simple database operations like transactions, right? There's not a lot of complex higher math involved. There's not, you know, these massive tables that have to get processed. The operations are pretty small and simple. BigQuery, on the other hand, is good for relatively infrequent, right? You're not going to be running hundreds of queries like this per second like you might for transactions in a busy system. But each of those actions could be a truly massive database operation. So that's what they're for. If your operations are small and simple, they belong on Spanner. If your operations are great, big, complicated things involving huge database tables, yeah, take it to BigQuery. Bounce back here for a second. Again, if both tables are very big, Google can make super large tables or slices of these cross tables combining all the fields. But eventually, those super large tables become too big even for BigQuery. So you can, if you dig around a little bit, you can find some links about BigQuery processes that fail. Let's see if I can find something here. Tables too large. Okay. So again, sometimes you can have data sets that are too big to process or a query too large. Basically, when Google's doing this operation, the size of the tables that it's dealing with internally, they're too big for Google to process in a real amount of time. So yeah, that does sometimes happen. Okay. So that's it. BigQuery and Spanner, F1. The key things you should know, right? I'll walk you through all these things again. So number one, Google's advertising system runs on extended SQL. It's not just SQL, but it's not quite NoSQL either. It's kind of this intermediate thing. Basically uses the same syntax, but data has special arrangements. F1 is the database that holds Google's advertisements. Spanner is the system that F1 is built. Spanner is the big database that kind of supports all of Google's database operations. And BigQuery is a specialized system for handling queries involving very large database tables. Okay, that's pretty much what you show. And then this comparison, sure, should know that. Okay, but you don't have to worry too much about knowing what database joins are, exactly how that process works. The point of this is just to give you a little bit of context about why BigQuery does have limits, okay, and where the limits come from. And for that matter, why ordinary organizations have limits, why database tables are a problem, and they might want to migrate that to BigQuery. Okay, so other stuff, terms and definitions, data marts and warehouses. So a data warehouse is all the data that belongs to a business organization. So think of it as just a big garage that you're throwing all your data in. That's the data warehouse. And a data mart is a particular subset of data in data warehouse. So typically it's for some specific functional area. For example, the accounting data mart, the finance data mart, whatever. And this results from sort of a natural growth process, right? Different departments are going to gather and manage their own data. Accounting has its own data that's largely kept in the accounting department. Marketing has its own data, largely kept in the marketing department. Now, if you combine your data in one big storage system, you know, that's pretty easy to do. Storage is never the problem. All you do, you get a bigger system, it's easy to file stuff away. But the problem is, in many cases, automating it and having data be retrievable quickly, that can be a big headache. For one, you can have different copies of the same data in different places. For example, finance might have some records of business partners that differ from the marketing information and vice versa. There's other ways errors could happen too. For example, one record could be entered incorrectly, one record could be in one system but not in another. They could have different formats for the same data. For example, another business, as it's referenced in the accounting system, might have a set of fields that's different from how it's referenced in the finance. So there's a lot of problems there, and there are also different permission levels across departments. So just because you can access the accounting database wouldn't necessarily mean you can access the finance database. So anytime you're doing some sort of automated querying of business capabilities that bridges multiple departments, it's going to be really tough to get those answers unless you've totally integrated your databases. So simple case, right? And this was one of the big trends of the 90s and the aughts, right? The first decade of this century was creating one common system to bring together all of these different database systems within an organization. And that's what ERP was. So we mentioned ERP a little while ago, I believe in the Amazon lecture, Amazon module rather. Enterprise resource planning systems integrate all the data from a business into one common system. And the reason why this is necessary, let's take a simple question. Okay, so we have a bicycle manufacturer. And the bicycle manufacturer has some resources, right? It has capacity, and it has orders, it has work in process, right? So work in process, stuff that's partially completed, and it has inventory of merch, right? Finished bicycles and components, okay? And it has pending orders. So these are all the information that the bicycle manufacturer has, right? Now a customer might ask a simple question, right? Some wholesaler asks, hey, can I order 500 bicycles to arrive by December 1st? Well, in order to answer that, the bicycle manager, oh, and we'll add on one thing, and if so, can you give me a quote? Right? Well, that's going to depend on a lot of things. So, number one, let's add this guy, suppliers, for components, primarily, right? Possibly other things, whatever. But let's just say components. We'll keep it simple. Let's do that. So this, you have a supplier as well. So what the business is going to do to answer this question, draw the arrows. Business has to answer the question, how many bicycles do I have on hand now? Okay. What else? How many partially finished ones do I have? Do I have components available in time to finish them? What's my shipping capacity by December 1st? Okay. If I don't have enough bicycles on hand, can I order components and have manufacturing capacity to meet this order? Okay, and that's just the manufacturing side of it. Then, of course, we also get into things, what credit terms should this customer get? Okay, so there are a lot of different systems involved in this. I might have to ask many suppliers. I might have to ask different manufacturing facilities that are under my umbrella. I got to talk to the accounting people to see, what sort of credit I have to give. I might also have to talk to finance and accounting to see if I can still get those components from the suppliers, even if they're available, right? If I'm not too far in debt, whatever. Yeah, there's a lot of questions. So again, back in the day, before ERP systems happened, the wholesaler would call up the manufacturer, and the manufacturer say, okay, we'll see what we can do about that, and we'll have the order back for you in a few days. And they'd call them up and do that. But nobody's going to wait a few days on a website, right? You want to be able to go to a website and right away say, hey, here's the order I'd like to make. Can I get this? Is it feasible? And what are the terms? And businesses want to have answers to those questions immediately. And in order to have those answers, you do need to have all this data integrated into one common system so the answers are right there. Okay, so where we are right now, most of the big businesses in the world have an ERP system, and even most medium and some small businesses do now as well. So what this does, where businesses once had many, many separate databases for different functional areas, now all those databases are being brought together under one umbrella, that is the ERP system, so that questions can get processed quicker. They don't have to be pushed specifically through other departments. And it also prevents the problem of inconsistencies across departmental databases. Essentially, any data that exists in ERP is only going to exist in one place, so you don't have the problem that one department might have a record that differs from another. Okay, so for example, right, we want a concrete example how one department could differ from another. Here's something. Okay, the accounting people know that the wholesaler has multiple unpaid orders, right? But of course, the manufacturing people might not know that. Or The manufacturing people might know that the wholesaler has just put in some large-scale orders, and should be charged, a different interest rate. But accounting might not. Okay, the manufacturing will have this information. Oh yeah, we have a bunch of orders pending from this wholesaler, but that information hasn't been transmitted from out of the manufacturing operation to the accounting operation yet. Okay, so again, these operations, they can have different data around the same things, and that can create problems. So in the first case, right, maybe you're not going to give that wholesaler any more credit, right? Imagine if this wholesaler is Sears and you're terrified that if you sell them some inventory, they're not going to be able to pay for it because they're on the verge of going bankrupt. That's a legitimate concern. Or, the manufacturing people might know, oh, they've added in a whole bunch of orders. They shouldn't have had that much credit in the first place. But, if accounting doesn't know that, yeah, that's a problem. Or the manufacturing gets all its gears in a row to make the order, and then accounting says, oh no, we can't give them credit for that because, they're over, they have too much of an obligation with us already. So these are typical problems that used to happen if you would try to push through an order quickly, and that's why it took a long time. But with ERP, the orders get processed much, much faster. Okay, so concrete example of that too, supply chain management. So supply chain management is the business function that's associated basically with getting goods in the right amount at the right time. So making sure that everything is where it needs to be at the right time. And it also manages all the associated transactions. Every time there's a handoff of goods, somebody has to say, yeah, I got it, and chances are they're paying for it as well. And it also tracks lots of data about past, present, future shipments. So things like doing analysis to figure out which travel routes are the best, which shipping mechanisms are the best, what are expected shipping times, anything that they care to look about, different routes, different weather, different business partners, whatever. Supply chain management looks at all that stuff. Now, as a function, supply chain management requires inputs from other departments. For example, for marketing, they need to know what's the demand for a product and what's the current trend. Is it going up? Is it going down? So supply chain people, they need to know how much capacity they have to have. And the way they know how much capacity they need to have is through expected demand for the products. Obviously, they interface with accounting for all these billing concerns. Anytime something gets paid in the system, that's accounting's job to know what's going on there. And of course, operations, where the work actually happens. So if there are new orders, supply chain people need to know what capacity is available to fulfill them. And, going forward in a reasonable amount of time too, maybe the next 6 months or the next year or two, they're going to need to know essentially what capacity is there now to fulfill new orders so that they can manage processes like bringing in components and getting things to where they need to be. Anyway, so an ERP, if it has high database consistency, right, basically anything that's changed in one part, all of the other copies of that data automatically get updated as well. That's going to allow very fast, very correct supply chain management decisions, because for any one question in the database, there's only one answer, and the answer will always be up to date. Okay, so we can talk about migrating supply chain to cloud. So if you have, as a scenario, that you have a business that's managing all its supply chain processes internally using its own hardware and software. Its goal is basically it wants to run that same system, but in the cloud. It doesn't want to deal with it anymore, right? It says, yeah, let's push this off to the cloud. It's too much of a hassle to keep this system up and running internally. We're going to put it somewhere else. So they might have as a big concern that the supply chain management system can't ever go offline, right? You can't just shut it down for a few days, because if you do that, you'll be basically shutting down your business for a few days, and that's going to cost you a lot of money. So big picture migration process, number one, clone each component from the internal system and make a copy of it in the cloud, what's called a virtual machine. So everything that the system does, all of those modular components, have them up and running in the cloud. Once that's done, you can copy your data to the cloud. So however many terabytes of data, or petabytes even, whatever you have, you get that all up in the cloud as well. And then you test it. So you test that the components work correctly, the system as a whole works correctly, it's doing what it's supposed to, it's not crashing, and it's giving you correct results. So when you're happy with how the cloud-based system works, then you use it and you shut down the internal system, right? So that's basically the process. You send the applications to the cloud, you send the data to the cloud, you test it. When it works well enough, you pull the plug on your internal system and start just using the cloud-based system. Okay, so related to that, we have this term virtual machine. What's a virtual machine? It is a computerized version of something. So example, you may have heard the term virtual server. That means a set of one or more machines and hardware that does all the same stuff that a single server can do. Okay, so it's likewise a virtual computer in the cloud or a virtual desktop like we have at the lab. It might be running applications on many different servers, but to you access it through one point, right? You go to UIC's virtual desktop and you access it, and it feels like you're only using one machine. So it's virtual in the sense it's not actually one distinct machine, but it does the equivalent, okay? Same kind of thing with virtual reality. It's not reality, but it brings all the components of reality together. And of course, machine just means a computer. So virtual machine, it's the equivalent of a computer and could include all the relevant hardware, software, or both. So anything that your computer could do, if you have a virtual copy of it in the cloud, yeah, that's a virtual machine, even though that computer's capabilities might be distributed over many, many different machines. So if your computer is running like 50 different applications in the cloud, each of those applications could be running on a separate piece of hardware. And cloud systems are built around these virtual machines. So users don't need to know the internal details of how the cloud is set up, and the cloud has the flexibility to assign or reassign resources wherever. It can run different applications on whatever hardware is appropriate at the moment. It doesn't always make sense in the cloud. In fact, it often doesn't, to have a machine that runs a whole lot of different applications. For cloud, it's often much better to run only one kind of application on a particular machine. That makes it a lot easier to track it for quality of service purposes. We'll talk more about that in the YouTube module. Okay, so back to our scenario. We know supply chain operations tend to generate lots of data, right? So there's transactions, there's shipment performance. So our business, they've decided to use both BigQuery and Spanner. And where it would make sense, for example, the workload division, well, again, if you're doing analytics on the shipment performance, chances are that's something you're going to use with BigQuery. Because why? Because you're going to have many different shipments over time with a lot of data that's perhaps at fairly short intervals. Those tables could be very, very large. On the other hand, transaction processing, that makes sense to run through Spanner, right? Because Spanner is designed to give that immediate consistency. So if one record shows that the company has paid for the shipment they received, we want that updated through the entire system. Other thing, timing and scale of database updates. So anything that needs to get updated very quickly, yeah, you probably want to run that on Spanner, right? On the other hand, something like analytics about shipment performance, that's usually the thing that it doesn't really have to be in real time, right? If you have 3 months of data, yeah, you run a query on it and you'd like to get the results reasonably quickly, but it doesn't have to be split second quickly because you're not going to implement those changes anything like split second quickly. Okay, but what you do need for transactions, you need that real-time consistency. You need that as soon as a transaction has gone through, it's reflected for every, every record that is somehow involved in that transaction. So once a package gets delivered, a shipment gets delivered, your record should show that it's been delivered. If it's been paid for, it should show that it's been paid for. There shouldn't be some kind of weird lag there where a shipment has been delivered, but then you have to wait a while to see if it's been paid for. You want that all to happen at the same time. Okay. Anyway, that brings us to the end of our lecture. I hope this has been beneficial for you. And if you're watching it on Thursday, well, then, or prior to this Thursday, then that's great. We'll be watching it then. We'll be talking about it in the review section, rather. All right. Let's stop that.